Hello everyone, my name is Lei Zhou. I'm going to introduce my work named Stochastic Boundary Adjustment for Efficient and Scalable 3D Reconstruction. First, I'm going to revisit the main computational steps of boundary adjustment as a background. In order to minimize the objective function, we linearize it to get the quadratic objective. Then we evaluate the minimizer by solving the normal equation. The normal equation can be simplified by shear complement, and we solve the reduced camera system instead. The reduced camera matrix embodies the connections between cameras, and its dimension is proportional to the camera number. Therefore, when the camera number grows, solving the reduced camera system would become the bottleneck of boundary adjustment. It is inefficient because it would ramp up the computational and memory consumption. It is neither scalable, because this step is indivisible, so we cannot apply parallel or distributed computing to it. In order to accelerate boundary adjustment, we propose to use clustering to decompose the reduced camera system. We start from the reformulation based on clustering. For example, for a physical point viewed by 4 cameras, we split the point into 4 virtual points for each camera. Besides, we enforce the equality of the 4 virtual points. Then the objective is reformulated as a new one about the virtual points, with additional equality constraints. The constraint new problem can be solved by Lagrangian duality, which introduces the Lagrangian multiplier and leads to a new reduced camera system. The advantage of the reformulation is that the reduced camera matrix is now block diagonal, so that the reduced camera system can be decomposed into as many subproblems as the cameras. But the disadvantage is that the Lagrangian multiplier is hard to evaluate, since it needs to compute the inverse of the Hessian matrix. Now the question is how to weigh the pros and cons. Therefore, we propose to solve the problem with chance-constraint relaxation when the equality constraints are enforced up to a probability. If we drop out a constraint, the corresponding Lagrangian multiplier will be eliminated. If we enforce the constraint of 2 virtual points, we bind them into one, so that the equality is always satisfied, and there is no need to evaluate the Lagrangian multiplier anymore. And we select the constraints randomly based on the sampled convex program. The remaining constraints shape the reduced camera system into cluster diagonal. It means that we can still decompose the reduced camera system into as many subproblems as clusters. The benefit of chance-constraint relaxation is that we do not need to evaluate the Lagrangian multiplier anymore. But at the same time, there is reduced feasibility in the solution because some of the constraints can be violated. Next, I will introduce 2 techniques to mitigate the negative effect of reduced feasibility. The first one is steepest descent correction. When the trust region is small, the Hessian matrix can be approximated by its diagonal, so we can evaluate the Lagrangian multiplier easily. The correction can remedy the approximation error caused by the reduced feasibility when the trust region is small. It also boosts the convergence rate. The second technique is stochastic graph clustering. We think about how to partition the cameras better. We consider 3 factors. First, we want to sample as many constraints as possible, so that more constraints can be satisfied. We use Louvain's algorithm, which joins the cameras from bottom to up, to contain as many camera connections in clusters as possible. Second, we make the clustering randomized, by joining the camera clusters based on a probabilistic distribution. Third, we want to limit the size of the clusters, so we stop joining clusters before they are too large. Here we visualize the clustering results. The cameras of the same cluster are in the same color. We evaluate the solvers on a SFM dataset, 1D SFM, and the SLAM dataset, KITTI. We compare Levenberg-Marquardt algorithm with either sparse or iterative linear solver, as well as dogleg algorithm. Our method is called STBA, a self-comparison. We also compare with our method using fixed clustering. We evaluate the solvers with performance profiling. The main idea is that, given a problem, we first find the minimum objective achieved by the solvers, and then relax the minimum objective by defining a threshold close to the objective. Then we compute the time a solver takes to reduce the objective to that threshold. If the time is small enough, we think the solver solves the problem successfully. The final score is the percentage of problems solved by the solver. If we require the solvers to reduce the loss by 90% or 99%, we find STBA is faster than Levenberg-Marquardt and dogleg by more than 5 times. But if we require it to reduce the loss by 99.9%, STBA is a little bit worse than LM methods, but it still outperforms dogleg. Both STBA and STBA fixed see a performance drop when tau decreases, because they have slower convergence near the stationary points. The reason is that clustering-based methods only utilize the second-order information within clusters during optimization, compared with LM or dogleg that use the full second-order information. However, STBA still performs much better than STBA fixed, thanks to the stochastic clustering strategy. The faster convergence of STBA is attributed to the lower per-iteration cost. To verify the scalability of STBA, we compare it with DBSCC, a state-of-the-art distributed bundle adjustment approach. STBA is faster than DBSCC by an order of magnitude because DBSCC requires heavy inner iterations to ensure convergence. We have released our codes on GitHub. Thank you for listening.